After studying this chapter, you will be able to purge a system with nitrogen, pressurize a system for leak detection, describe different methods of leak detection, explain the use of vacuum pumps and the evacuation procedures, understand procedures for charging systems with refrigerant, be able to explain the recovery and recycle procedures. Nitrogen and carbon dioxide are inert, meaning they do not support combustion. They are high-pressure gases used to purge the system while brazing or pressurize the system for leak detection. Never use oxygen to pressurize the system. It explodes on contact with compressor oil. Never start the compressor when the system contains nitrogen or carbon dioxide. A special pressure regulator is used when working with high-pressure nitrogen or carbon dioxide gases. Flow pressure should not exceed 300 pounds gauge. Clockwise movement of the flow adjustment increases flow pressure, and counterclockwise decreases flow pressure. The middle hose of the gauge manifold is attached to the outlet of the pressure regulator. Control of flow pressure and direction of gas flow is transferred to the gauge manifold. Purging the system with nitrogen while brazing keeps the system clean and reduces the time required for evacuation. A continuous flow of nitrogen at 2 to 3 pounds pushes atmospheric air and moisture out of the system to prevent internal oxidation. The nitrogen is vented to the atmosphere to prevent pressure buildup. When the system is completely assembled, the entire system is pressurized to 300 pounds for leak testing. Large leaks are located by listening for a whistling sound. Small leaks are pinpointed by using soap bubbles. The nitrogen is released to the atmosphere when all leaks are located and repaired. A dauber or squirt bottle makes a handy soap dispenser for leak detection. Be generous with the solution and allow time for the small bubbles to appear. A concentrated dishwashing liquid works fine when diluted with equal parts of water. The bubble test is the #1 method for leak detection, but adequate system pressure is required to blow bubbles. The halide torch is a sensitive refrigerant leak detector. It does not detect nitrogen or carbon dioxide. The blue flame draws air and refrigerant from the suspected leak site up the sniffer hose and into the flame. When burning refrigerant in the presence of copper, the flame color changes from blue to green. Because refrigerant is heavier than air, begin checking at the top and work downward. Check each potential leak site by slowly passing the sniffer hose over it while observing the flame color. Always check tunnels and confined areas with the halide torch before entry. Electronic leak detectors will respond with an audible alarm to all halogen-based refrigerants, including CFCs, HCFCs, and HFCs. The beeping signal increases in speed and frequency as the leak source is approached. Always begin at the highest point and work downward. Some oil circulates with the refrigerant in most systems. Evidence of oil on fittings, parts, or the floor is a good indicator of a refrigerant leak that must be repaired. Always clean up old oil spills and keep a watchful eye for evidence of new oil. Before evacuation, the system's internal pressure must be reduced to atmospheric. The vacuum pump draws all vapor out of the system, reducing its internal pressure to a very low vacuum. A special oil is required for vacuum pumps, and an oil change is recommended before each use. The amount of time required to evacuate a system is strictly a matter of judgment. A large system requires more time on the vacuum pump than a small system. Time must be allowed to pull a vacuum in all parts of the system, and for moisture to work its way out of the oil in the compressor crankcase. Moisture located in traps and in the compressor oil is the last to be removed. Heat lamps can be used to drive moisture out of the system when evacuating. Never use a torch or live steam for this purpose. A standing vacuum test is performed by waiting a few minutes after performing a thorough vacuum. Holding a 30-inch vacuum for 30 minutes does not mean the system is leak-proof. It means the system is leak-proof at 15 pounds pressure. Charge the system to 200 pounds and leaks may appear. Never use the vacuum pump as a leak detection device. Charging the system with refrigerant vapor at the suction service valve while the system is running is an acceptable and safe procedure. The manifold valve must be closed periodically to check true suction pressure. For refrigerant to enter the suction service valve, the cylinder pressure must be higher than the suction pressure. The refrigerant boils inside the cylinder, absorbing heat from the remaining liquid. The cylinder becomes colder and pressure is lower. Placing the cylinder in a bucket of hot water increases cylinder pressure. Do not use a torch or live steam. Charging by the sight glass is an acceptable procedure if done properly. When the bubbles go away or become very scarce, the liquid level inside the receiver just covers the dip tube inlet. More refrigerant is required to bring the liquid level in the receiver up to about 1/4 to 1/3 full. This extra refrigerant is normally a judgment call and not critical. Use care not to overcharge. The system data plate discloses important information. When the refrigerant and exact amount of charge is known, the technician can weigh the refrigerant into the system. Liquid charging into the suction service valve requires skill and caution. The suction hand valve on the gauge manifold is used to carefully meter the liquid. Gauge pressure should not exceed 20 pounds gauge above actual suction pressure. When metering liquid, observe the frost line on the blue hose. When the frost line reaches the suction service valve, close the manifold valve. Frost will immediately disappear and you can check actual suction pressure. Repeat this procedure until charging is complete. Graduated charging cylinders are often used for charging systems having less than 5 pounds of refrigerant. When the exact weight and type are known, this device can be used to accurately weigh the charge into the system as a vapor or a liquid. CFC and HCFC refrigerants are known to damage the ozone layer. Chlorine is the primary culprit. CFCs are very stable, chlorine-containing compounds that do not break up in the atmosphere as do other, less stable refrigerants. Ozone depletion potential, or ODP, is a measurement of a refrigerant's ability to destroy ozones. CFCs have the highest ODP. HCFCs have a hydrogen atom in the molecule, making the molecule less stable. Therefore, HCFCs tend to break up quickly when released to the atmosphere, and they have a low ODP. HFCs contain no chlorine, so they have no ozone depletion potential. Recovery cylinders are color-coded and have yellow tops and shoulders with gray bottoms. The cylinder has 2 valves labeled liquid and vapor for obtaining liquid without inverting the cylinder. Recovery equipment is designed to remove refrigerant from a system and transfer the liquid to a refillable cylinder. When repairs are completed, the refrigerant may be returned to the system. This recovery procedure is mandated by federal law to prevent release to the atmosphere. Refrigerant recovery is accomplished by connecting the gauge manifold to the suction and discharge service valves, then connecting the middle or yellow hose to the recovery unit. The recovery unit is then turned on. The recovery cylinder is normally placed on a scale to prevent overfilling. If the recovery equipment was manufactured before November the 15th of 93, the refrigerant must be recovered to the levels indicated in the middle column. If the recovery equipment was manufactured after November the 15th of 93, the refrigerant must be recovered to the levels indicated in the last column. After a pump down to capture liquid in the receiver inlet service valve must be closed. Vapor trapped in the condenser and hot gas discharge line must be removed by the recovery method. Repairs can then be performed on either side of the system. This slide illustrates the passive recovery method for capillary tube systems when the compressor is not operating. Saddle valves are installed on both sides of the system. Connect the hoses and open both saddle valves. Refrigerant will migrate and condense inside the cold recovery cylinder. This method recovers about 80% of the system refrigerant and is EPA approved. This slide illustrates the passive recovery method for a capillary tube system with the compressor operating. A saddle valve is installed on the high pressure side only. The cold recovery cylinder will condense about 90% of the system refrigerant. This procedure is EPA approved. Active recovery involves using a self-contained, independent recovery system. Refrigerant is withdrawn from the refrigeration system as a vapor, condensed to a liquid, and then stored in a refillable cylinder. Always use a scale to prevent overfilling the cylinder. The refrigeration compressor does not operate during the recovery procedures. Inside a recycle unit, a liquid pump pulls liquid from the bottom of the cylinder via the dip tube and liquid valve. The liquid refrigerant passes through a replaceable core filter dryer and is returned to the top of the cylinder via the vapor valve. Recirculation of the liquid refrigerant through the filter dryer removes moisture and contaminants and may require several hours to accomplish this purpose. A recycle unit uses a pump to draw liquid refrigerant from the bottom of the cylinder and circulate it through a replaceable core filter dryer to remove moisture and contaminants from the refrigerant. The filter dryer does not capture all the contaminants in one pass. It may require 4 hours of recirculation and a change of dryer cores to clean the refrigerant.